Why?
She doesn't want to ruin her weekend. Alright. Okay. Well, let's just see with the rest of the class. Class, would you like your results on Friday or Tuesday?
Friday. Okay, you get the on the.
Yes, I can give you yours on Tuesday if you want. Don't have to. I can just black yours out or something. Okay, Dropbox, DIFC, Physics, Part 5, Fields.
Total is 227 gigabytes.
Well, I have to remember I said my laptop broke, so I had to erase everything on it, so now I have lots of free space.
Are we going to get a local?
No.
What?
The simple fact is I don't have the time to copy the questions from my slides into the Word document. That's just the honest truth. I mean, I barely have time to actually correct your work. I still have to correct your essay.
You're busy.
I'm too busy. The problem's my co-workers. Yeah, they can't do things by themselves. They're helpless. Just, they're like, oh, Stephen, I need help with this. I can't do this. Help me with this. How do you do this? Huh? They don't believe me. They say, oh, how do I do this in Excel? I'm like, oh, I don't know. I'm not very good at computers. They won't believe me. Okay, so we'll continue now. Electric fields. You got that? Electric fields? Okay. Continue? Yep. No. Yep. Okay. This first lesson's not. Wait, this feels wrong. We don't usually start with electric fields, do we? Lecture 1, electric fields. Oh, okay. I thought I would have started with magnets. Okay, anyways. Oh yeah, well I suppose this is actually kind of easy because you would have done this in chemistry. You know that an electric charge is a basic property of No, you don't necessarily have to write this down because I might just be telling you something which you know from chemistry that's really obvious, okay? So electric charge is a property of electrons, protons, and other particles. And you probably know this. Electrons are negatively charged while protons are positively charged. Now, did you know this already? I'm sure you did from chemistry. So there's not necessarily anything to write down, except, well, I don't know. You all knew that charge is a basic property. Like it's like what I mean by basic property is that it's like something like mass or volume. It's a feature, the property of the atom. You understand what I mean by that? That it's a property. So I suppose you can just write down it's a basic property. Electric charge is a basic property. Yeah. Okay, let's continue now. Get to something interesting. And again, you might already. Now, I'm sure you must know this from chemistry. Things that are negatively charged and things that are positively charged, they pull on each other. Attract, yeah. And then things, this is what makes electrons and protons stick together. You got your proton, you got your electron, they're stuck together. Things that have the same charge, what happens? They repel, yeah. But why did you learn this? This is like chemistry week 1, is it? Semester 1, week 1, chemistry.
Week 2, week 2. Okay, week 2.
So this is just called the law of charges. Maybe you just even want to write that down. Law of charges. Opposites attract, like repels.
Attract with same power.
What do you mean?
I have proton. I am proton. proton, you are the electron. We are attract each other. Then the power is same.
The force.
The force is
The same. Not the power. Power is different meaning. Okay. So, anyways, again, you know this from chemistry. It's quite boring. Not interesting. It's law of charges. Okay, now we're getting into something new, something which you haven't seen before. We have this thing called an electric field, and it's a vector field. So before I even continue with the definition, I have to explain what I mean by a vector field. So I'll give you two examples. I'll give you something first as an example. Here is something which you might call a scalar field. So let's imagine we have a room, and let's just imagine that we say the room is at 20 Celsius. But of course we know that not everywhere in the room is 20 Celsius. Like imagine, imagine I have a heater here. And imagine I have a window here. Okay, we'll say the window's open or something like that. Not a great window. Is it 20 Celsius everywhere? No. Like what would you expect like here? At points, if I look at points here, what would it be?
30.
It could be 25 Celsius. And if I was to look at a point here, at this point, what might the temperature be?
17.
Yeah, maybe 15 or 17 or whatever. So this is called a scalar field. The meaning is you have scalars, which are numbers, but it's a different number at a different location. It's not constant, you know. So up here, maybe this could be a 30. And down here on the ground by the window, this could be maybe a 10. So scalar because it's a number, and field in maths and physics, fields means like a space. And the idea is at different places we have different scalars. Okay, well that's a scalar field. So what do you think a vector field might be? What could that be? Yeah, so what might be an example? Simple example that you know.
Vacuum.
Which one?
Vacuum.
A what?
Vacuum.
Bacon?
Vacuum. Vacuum.
Vacuum?
Vacuum.
Vacuum. Not bacon. Quite different. A vacuum doesn't have anything in it though. Let me give you an example. So, if I scroll down. So imagine we're looking from the top. Say this is the north, this is the south, this is the east, this is the west, and there's a wall here. And here's my man here standing by the wall. So you understand if there's a wind blowing from the north, we can represent the force by a vector. But what about here? Is it the same force? No. In fact, there might not even be any force. And then you might have a little force, and then more here, and then more here. In fact, you can kind of appreciate that at different places the wind might be blowing in a different direction because of things like the wall. So this is a vector field because at different locations we have different vectors. Yeah? So are we happy with the meaning of vector field? Do we get the idea? So when we say an electric field is a vector field, that means we have a direction that shows where a small positive charge will move. A bit like the wind. I'll give you an example. Like, let's say,
I think you need.
oh no, the update I keep postponing. I need to eventually do it. Let me give you an example. Let's say I have an electron here, and I put a proton here. Or let's say I have many electrons here, and I put a proton here. Which way does the proton move? To the right. Now, if the proton was here, would it move faster or slower to the right?
Faster.
Faster. And if the proton was over here?
Slower.
Slower. And if the proton was here?
Same.
Yeah, it's about the same. So you see the way I'm drawing these arrows? These arrows are called the electric field. They show you the way a small positive charge would move in the field. You know, you imagine if I put a small positive charge, which way would it move? That's what the vector field is. It shows you the way a small positive charge would move.
Then the electron doesn't move.
Oh, well, in real life it does. That's why I said if you have many electrons, then it's too hard for the proton to pull it. Okay, so this you need to write down. Okay, got that? Yeah? It's only one sentence. Continue?
Yep.
Yeah. Continue? Right. So here's an example of an electric field. If you think about it, it really does make sense. If I was to put a small positive charge here, it makes sense that it gets pushed away. Or if I put it here, it gets pushed away. And if I was to put it like here, it would be pushed away from the positive and pulled to the negative, so the positive charge would go in here. And likewise, if I put the positive charge here, it would move into the negative. So this is an example of an electric field around a positive and a negative charge. You just need to imagine where the little positive charge would move. So a little positive charge would move like that. Yeah.
So it's always positive goes negative, not negative goes
Oh yeah. And the definition is always, for the field, what way would a positive charge move? So interestingly, if I have a small negative charge, like if I put a small negative charge here, which way would it move? Left or right? What? To the right. So the negative charge moves against the field, and the positive charge moves with the field. Yeah. I think it's worthwhile drawing this as an example.
The load of proton.
Huh?
The load of proton.
To get the picture?
Yeah.
There are other ways to get the picture, but you can imagine as if it's loads of little protons or something. Yeah? Continue? So, how do we measure charge? Well, we use a new unit. But in chemistry, how do you measure charge? What do you say? Well, what do you say the charge of an electron is? Yeah, -1. In chemistry, though.
-1.6.
No, I don't think you say this in chemistry, do you?
Yeah.
I I don't think you do. I think in chemistry you just say the charge is -1 or +1.
Yeah.
Yeah. But we have an actual unit which you're mentioning that we use to measure charge. We measure charge using a unit called the Coulomb. And it's a standard unit, SI unit, of electric charge. And the definition of the Coulomb is the charge when 1 amp runs for 1 second. So if you have 1 amp of current for 1 second, you say you have 1 Coulomb of charge. This is the definition. Quite a common definition in the exam. What is the Coulomb? It's 1 amp for 1 second makes 1 Coulomb of charge. Yes?
Electron? Or
No, electron is much smaller than this. No. You see, this is the problem. This isn't the same as what you would say in chemistry. So when you say in chemistry +1, it's not meaning 1 Coulomb.
like circle.
What do you mean?
Coulomb. The definition of Coulomb.
Like a circle? What do you mean?
Electric. No.
Oh, like the circuit?
Yeah.
Oh yes. Yes it is, yes.
Same thing, huh?
Yes. Okay, continue? Yeah. Right. So, now, let me actually give you some numbers. So the charge of a proton, which you call +1 in chemistry, is exactly this many coulombs. Now that's quite small, 10 to the -19 coulombs. 1.602 times 10 to the -19 coulombs. That's the charge of a proton. Yeah?
If I have 1 proton.
That's how much charge you have. Yeah. You should write this down because you'll need it for some of the questions, I'm sure. Yeah? Okay. Obviously the electron is going to be the same thing but with a minus. And the neutron?
Yeah.
Yeah? Now, by the way, the mass of a proton, which you'll need for some of the questions, have you done this in chemistry, the mass of a proton, or not? No? The mass of a proton is obviously quite small, and so for electron, and so for neutron as well. Can you note these values, please?
You have to memorize these.
Oh, no. Well, life isn't that hard.
You memorize.
No, I never remember these because they're all on the calculator. I think this is like constants. I think this is constant 1, 2, and 3 on the calculator. I think this one is like 23.
Memorize that number.
That's all that's necessary, yeah. Okay, you got that over there? Yeah? Yeah, guys? Yeah, you have this? Yeah? Okay. Now, often this number is simply written as E, and in fact it's on your calculator. I think it's constant 23 or 27 or something. If you look at your lid, look at the lid there. Is it 23 or 27? 23.
Should know.
It'll be in the formula book as well. So, different parts of the field will be stronger or weaker than other parts. After all, the small positive charge will fly away faster if it's nearer to another large positive charge. So we have this idea now that we kind of need to measure how strong the field is. So if you look at the picture you drew earlier, where do you think the field will be the strongest? Probably right beside the charge. And the weakest? There you go. Yeah, or far away from them. So we have this thing called electric field strength. It's a way to measure how strong the field is. And the definition of electric field strength, E, is defined as the force per charge, or simply the field strength is the force divided by the charge of the particle, the little particle. So if you have a little particle of charge Q and you put it in the field and it feels a force, then we say the strength is the force divided by the Q. It's the force per charge, the newtons per Coulomb.
The force is by a particle.
Yeah, the particle will feel a force. It gets pushed or pulled. So if you take this force and divide it by the particle's charge, you have what's called the field strength.
Charge is bigger than means field strongest is smaller.
Well, what usually happens is if you put a bigger charge in, you get a bigger force. So the electric field strength will be usually constant at the point. Yeah. Well, if you take the charge and put in a field, it will move. So it's the force it feels in the field. You got that? Yeah. Yeah? Continue?
If I have electric field,
Yeah.
this electric field strength doesn't change.
Well, no, you can do things to change it. But usually if you look at one point in the field, it doesn't change. Yeah. But we'll see actually there's different ways to make the field and their strength can be adjusted. Okay. Let's have a look at an example. Current runs through a copper wire and the electric field strength is 10 to the minus 25 newtons per coulomb at a distance from the wire. What is the force felt on an electron at this distance from the wire? So just to draw the picture, you have a current here. Now if this is a positive charge, and let's say you have here your electron which is negative, it should be pulled towards the positive charge. Okay? And I tell you that the electric field strength here is equal to 10 to the minus 25 newtons per coulomb. So what that means is for every coulomb you have, its force it experiences will be 10 to the minus 25 newtons. But my question actually is, what is the force? Well, that's easy because there's only one formula today. E equals F over Q. So that means F equals EQ. And do we know the E? Yeah. And do we know the Q?
Yeah.
We do. It's the charge of an electron, which is actually on the calculator if you don't have it written down. Let me open up the calculator. Maybe you could just type it in while it's opening. It's constant 23. You all know how to use your calculator, the constants. Oh, Bruce. Type shift 7
Shift 7.
and then 23.
Oh, yeah.
You get it? You don't have. You surely have the charge of an electron on that.
Yeah, but I couldn't find that.
Shift 723 times 10 to the power of minus 25. You get this tiny force. 1.6 10 to the minus 44 newtons. Okay, is that okay, that one? Did you find it? Yeah. Yep, okay. Next one. That's an easy one. Let's look at the next one. Okay. An electron is placed near 3 protons, and the 3 protons produce an electric field. And the strength of the field is that. What is the acceleration of the electron? So, let me just draw that. You've got 3 protons, 1, 2, 3. You've got an electron, and what will happen to the electron? It will move towards the protons. And my question is, what is the acceleration of this electron that's moving to the 3 protons? I think you could do this one. Again, we just have one formula for today's lesson. So I'll give you a moment to try and figure that out. Which electron 9.11, isn't it? I don't know. Shall I do it now? I see it's typing still. Yes, the door is locked. Hang on a second.
Hi, excuse me.
Hey,
Hey.
need me or them?
The workbook,
Which one?
the exam. Yeah.
Maths or physics?
Physics.
Do you have them downstairs?
Yeah.
Oh, great, okay. You can let them know that if they were to go to Moodle, oh no, not for physics, I was thinking maths. No, that's fine, great.
Give them a message.
No, actually it was for the maths and the physics, so it's alright. The full house?
Well, that's 12.
Oh, okay, alright. Right, you got an answer here?
0.00.
Okay, let's see. Show, what did you do to your calculator? You're strange. Right, let's have a look. So, we know that F equals MA.
Yeah.
So A equals F over M. Now, do we know the M?
Yeah.
We do. Do we know the F?
Yeah.
Well, we could know it. So, yeah, E equals F over Q. So F equals EQ. So, the acceleration would be EQ over M. Now, wait. This Q here, is it for the electrons or for the protons?
Electrons.
Good. And the M here, is it for the electron or the proton? Electron. Okay. So, taking out the old calculator, what did I say the E was? 1.4110. Okay. And now I need to multiply that by the charge of an electron, divided by mass of an electron, which is constant number 3. Oh no.
Yeah.
Right. So I get 2.48 10 to the minus 13 meters per second. Yeah? I hope some of you got that. What? Give me your calculator. What did you do? I don't know what you... No, shh. You see, you're like my co-workers. Help me. I don't know what to do. How do I fix this? I forgot my password. Okay. There you go.
Oh, how good is that?
Magic. Yeah, well, I said in the question actually to call positive to mean in and negative to mean out. So actually, because it's going in, I want you to make this positive then. Yeah? Is it okay? I mean, I can continue or... Yeah. A small dust particle of 1 milligram and charge minus 100 electrons is placed between two horizontal plates that produce an electric field. The charge is held in balance between the plates and does not fall. How strong is the field? So let me just draw that for you. What you've got two plates, you've got a little negative charge here, okay, and you've got a field here, and this field causes the particle to want to go up. But also the particle has another force wanting it to go down. What force is that? The weight, yeah. And in the question they are in balance. They're balanced. And my question then is, how strong is the field? So I want to know what's the E here at this point. Okay? So, let me try, again, I think you could do this. It's using the same formula, E equals F over Q. Yeah?
How I know if the plate is like this or like this?
When we say horizontal plates, we mean the plate is lying horizontally. So it's like this, and we would describe this as being a vertical plate. Yeah? Got an answer to Wookie? Yeah?
6.12 by 10 to the minus 10 to the 14.
Are you sure?
Yeah.
Are you very sure?
100%.
Oh, it'd be funny if you're wrong. Okay, let's calculate. So, tell me then, Wookie, what was the trick here? What you need to do? E equals F over Q. Do we know Q? Yes. Yes. Do we know F?
Yes.
Well, we could know it.
Yeah.
How could we know it?
F equals weight.
Yeah. Right. Do we know the mass,
Yeah.
the G,
Yeah.
and the Q? Okay. So, what's the mass here?
1
A milligram.
Oh.
One.
I'm wrong. 10
But you said you were 100% sure.
Oh.
You see, what have you learned? You're never 100% sure in life. Okay, a milligram is
10 to the minus 6.
1,000 of 1,000. Yeah, 10 to the minus 6 times 9.81 over 100. 100e.
Yeah.
Roughly the same.
Close.
6.12 times 10 to the 11 newtons per Coulomb. Okay, never say you're 100% sure of anything. Huh? What's wrong?
Milli is 10 to the power negative.
No, it's 10 to the minus 3. But the problem is the unit we should be using is kilogram,
Oh, yeah.
which is 1,000.
That's minus.
Yeah, see, a gram is actually 10 to the minus 3 kilograms.
Oh.
So a milligram is 10 to the minus 3 10 to the minus 3 kilograms. Yeah. Okay, you have that one? Yeah. Okay, let's see. No, that's stupid. Well, it's just answer it. A proton and a proton are a distance apart. Proton here. What is the field strength in the middle? Equidistance between the protons. Proton, and you're in the middle. What's the field strength there? Nothing, yeah, why?
0. 1 cancel.
Cancelled, yes.
There's no field like.
Yeah, they cancel. In fact, if you have two fields that are in opposite directions, they can cancel. Like forces. You know, if you pull left and you pull right, then you can have nothing. Yeah. Okay. Just the 4 questions. I would like you to try these for a few minutes and then we'll start the next lesson. Can I close the video? Just the video? Let's see. Hang on, let me just close this.